Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use the what's called a shell method to find an integration to find the volume of a solid or revolution. So the example we're going to do here is number 2 in section 6.2 in the current calculus text I'm using. We're going to look at the function defined by y equals 2 minus x squared over 4. We're going to look at it out to x equals 2, and we're going to calculate the volume you get when we take this surface area and revolve it about the y-axis. So you always start these problems by drawing some sort of differential element. I'm going to start with a rectangle. Now, the width of this element you could label as a dx or a delta x. It kind of depends on how you plan on working the problem. If you're going to do this numerically using a computer and a finite number of elements here, like 10 or 20 or something, you would label it as a delta x. I'm going to use integration. So when you use integration, you're inherently using an infinite number of rectangles. So the most appropriate thing to label this would be a dx. That'd be perfectly fine. No doubt we're going to need the length of that rectangle. The length of that rectangle is defined by the function value, 2 minus x squared over 2. Now, if we were looking for the area, we would take the length times dx, but we're not. We're looking for the volume of the solid or revolution. So what you have to imagine now is this rectangular area being revolved about the y-axis, like so. And what that's going to give us is a geometry that most people call a shell. I'm going to draw it over here. We're going to get this geometry. It's going to look something like this. Now, the thickness of that shell, there's your dx. The height of that shell is the length of this rectangle. There's your 2 minus x squared over 2. It's very important to realize this thing is hollow. It's kind of like a pop can with the top and bottom cut off. It's not a solid shell. Now, to get the volume, there's a couple ways to do it. I like to take this. Imagine taking this surface area, which is going to be 2 minus x squared over 2 times dx, and then multiplying by the distance around. That takes that surface area and it turns it into a volume. Now, the distance around is 2 pi r because that's one circumference. So 2 pi, and the r is that distance, which is x. So in this example, 2 pi x is the distance around, that's one circumference, times the area of the circle, or of this rectangle, gives you the volume of this thin shell. You can also get that by, if you were to imagine cutting this and flattening it out, you'd have a rectangle. The thickness of the rectangle, that's your dx. This distance is the 2 pi r, or in this case 2 pi x. And this distance would be the 2 minus x squared over 2. And then you're getting the volume by length times width times depth. Right? Now, this gives a differential volume, dV, because this is a dx. The total volume we would get we would add these all up, 2 pi x times 2 minus x squared over 2 dx, with x in this example running from 0 to 2. And now it's just a matter of working out the integral. So the 2 pi, like always, can come out in front. And then we're going to have the integral of 2x, which is going to be just x squared. By the time we take 2x, x dx integrates to x squared over 2. The other integral here is going to be minus x squared over 2 dx. That's going to integrate to minus x to the third over 3, and there's a 2 sitting there, so I'm going to make that a 6. That's evaluated from 0 to 2. So I'm going to take a moment here and look this over and make sure I did this right. All right, so the 2 pi comes out in front. That's this. Integral of x times 2, so the integral of x dx is x squared over 2. The 2's will cancel, leaving us with just the x squared. Integral of x to the third is x. Ooh, see, I'm glad I checked that. This product is x to the third, which is going to integrate to x to the fourth over 4. And when we take that 4, and there's another 2 sitting here, that's going to become an 8. I think that's good at that point. Just making sure everybody's paying attention who's watching this. I think that's good. All right, so now what we're going to get is 2 pi times. Now we're going to put 2 here, which is going to be 4 minus. Now if we take 2 to the 4th, 8/16 over 8, 2. Well, I guess that's 2. Yep. Minus, putting 0 in, we get 0 minus 0. So we end up with 4 pi cubic units for the volume of that shell. Now, whether or not you end up with a shell or a disc or a washer, it depends on the type of elements you're setting these up with. In this particular example, I don't know why you'd want to, but you could set this up using the disc method. I'm just going to take a moment and talk about what it would look like a little bit. If we drew a horizontal rectangle and then revolve that about the y-axis, we'd get a disc. The area would be pi times r squared, and then times dy would give you the volume. But you'd have to recognize something. The radius of that disk is going to change how it's defined when we move up into this region, because here this rectangle has a length 2. That's true everywhere up to that point. Once we move up inside of here, the rectangle's length is now defined by x, and you'd have to solve this equation for x and work it with 2 integrals. And I'm not going to do that in this video. I just want to talk a little bit about what the 2 different setups would look like. If you did use a horizontal rectangle, you would need 2 integrals because the length of this rectangle changes once you get above this point. And the geometry would be a disk, so the volume would be pi times radius squared times dy. Anyway, I hope this example helps demonstrate how to set up an integral to find a volume. Have a great day.